Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new, exciting video, all math-based, of course. And as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside. We are going to look at section 6.5 in the Big Ideas Math Integrated Math 2 textbook on the triangle mid-segment theorem. If you want to be caught up with all the other things I've done in chapter 6 so far, section 6.1 to 6.4, other things involving triangles and proofs, go and check out the description section down below. You will find the link to the IM2 Big Ideas Math playlist, as well as, for this specific section, the textbook PDF and graph paper if we need it, and the timestamps to all of the problems by section, including the lecture overview that I'm going to begin with as I generally do. So strap in, let's get going, shall we? And we are going to begin with said lecture and figure out how to use mid-segments of triangles in the coordinate plane. Okay, so graphs will be used, and use the triangle mid-segment theorem to find distances. This one's going to be pretty okay for you guys. As long as you know proportions, should be pretty okay. All right. Well, actually, no, this isn't even, yeah, I was thinking side splitter theorem. No, this will be pretty good. Okay, the mid-segment of a triangle is a segment that connects the midpoints of two sides of the triangle. So we got a mid-segment here, MP, and PN, and NM, because they are all, MP and N are all midpoints of the sides of the triangle. Every triangle has three mid-segments, which form the mid-segment triangle. So triangle MPN is called the mid-segment triangle. The mid-segments of I just said all that stuff there. Now, what they're showing is stuff that we should therefore also know and understand, is that if this is a midpoint, it's dividing its two congruent parts. So when they call something a mid-segment, they are segments from the midpoint. So we should know congruency here at the very least. What these lengths are, we'll find out soon enough, I'm sure. Oh, here it is. Using mid-segments in the coordinate plane, in triangle JKL, here's JKL, show that the mid-segment MN is parallel to segment JL, and that the length of MN is equal to half the length of JL. So one of the first things we're going to learn, and this isn't the proof, but it applies, we're going to show that this mid-segment is half of the side that it's parallel to, the side of the triangle. So they're going to use a form of, down below, eventually they're going to use a form of Pythagorean theorem or the distance formula to show that. But before that, they need to find the midpoints themselves. Midpoint of M is the average of the x and y values of j and k. So they add those numbers divided by 2. They get negative 4, 3. Remember, this point wouldn't have been plotted yet. And you see me do it in this other way where I'll like rise and run and take half of that rise and run, and that'll get me there. And I'll probably stick to that if I have the graph. And then n is the same thing. It's going to be at 0, 2. So now we can use those to show that the slopes are going to be the same, first of all. I mentioned they were parallel. It did not mention that yet, but they will be parallel. Notice they both have a slope of negative 1/4. You can either count that down 1/4, down 2/8 kind of thing, or compute it with y2 minus y1 over x2 minus x1. So they are parallel. Now the distance formula is the square root of the difference in x squared plus the difference in y squared. You get the square root of 17 for the length of segment MN, and 2 root 17, which is simplified from root 68 for the length of segment JL. So they're showing that it's also half of it, because root 17 is half of 2 root 17, which is pretty cool. So they didn't prove it here, I'm imagining, and I don't know if I missed a theorem. I didn't, so they'll either mention the theorems on the next page, or it's something that we get to prove later, or a little bit of both. We get to prove as they show the theorem. Here's another one if you want to take a look at it, but of course we're going to do our own problems, I'm sure, with exactly that. Okay, so here's the theorem itself, the triangle mid-segment theorem. The segment connecting the midpoints of two sides of a triangle is parallel to the third side, and it is half as long as that side. So DE is parallel to AC as far as segments go, and the length of DE is half the length of segment AC. Now that's just one of the mid-segments. This is true for any of the mid-segments, is what they're saying. They're saying the midpoints of two sides of any two sides. Of any two sides. It doesn't have to be these ones specifically. If we drew a mid-segment here, this would be parallel to this, and it would be half that length as well. Proof, example 2, page 373. I guess we get to go over that proof as well. They're going to do things with triangles. Okay, Yeah, I'm trying to see what else we'll do with the proof stuff. Oh, never mind. We get to prove the theorem here. This is page 373, apparently. All right, so a proof for this one, if we want to take a look at it, they're going to use graphing form to show that it is half of the length and to show that it is parallel. By drawing a triangle flat against this, they end up providing the midpoints of DE using algebra with coordinates. They find D's point is QR and E is this stuff right here. Basically, again, doing midpoints, but with algebra based on whatever lengths they have here. And they use 2 in them so that they can divide it by 2 eventually. And then they just show that basically these have the exact same height of R here, which means they have a slope of 0, just like this has a slope of 0, which shows that parallelness. And this isn't using any numbers. This is just using letters. And you can lie any side of a triangle flat. It's fine. So they show it with this one. And then they... Yeah, I thought they were going to do a congruent triangle proof thing, but I suppose that's to show something else later. And then they show that it's half the length. They say use the ruler postulate. It's basically a way of saying find this distance by subtraction. You don't need Pythagorean theorem or distance formula because they're horizontal distances. And they just show that one of the lengths is p while the other length is 2p. So you can look more at that if you'd like to. I was hoping to find a triangle proof with it. Okay, let's do an example where we're actually using the theorem itself. The triangles are used for strength in roof trusses. In the diagram, segment UV, let me get a brighter marker for that. Segment UV and segment VW are mid-segments of triangle RST. So if UV is a mid-segment, that means use the midpoint of segment SR, which means these are congruent. And if VW is a mid-segment, then W is a midpoint of RT, like that. And V must be a midpoint over here, which means these are congruent as well. We're missing the third mid-segment. That's fine, but these are all 3 midpoints. We just don't have they call it mid-segment triangle or mid-triangle? I forget what they called it. They say find UV and RS. So UV is this length right here. Now UV should be half the length of RT. RT is 90, UV is the one that's parallel to 90. So being half of RT, half of 90 is 45 inches as they put. And then find the length of RS. RS is this entire length right here. It would be 2 of these guys. Now one of these guys is 57, VW being the one parallel to this one. It's mid-segment. Over here we got a double 57 and we get 114 inches. Okay, using the triangle mid-segment theorem here, hopefully you can kind of see this picture for what it is, a triangle, and then a mid-segment triangle. In the kaleidoscope image, AE is congruent to BE. Let's see what I can mark this. AE is congruent to BE, like that, and AD is congruent to CD. Show that CB is parallel to DE. This is the kind of stuff where I would use more of those proof, like the 2-column proof things. They made it as a paragraph proof, and I'll use what they explained. So they're showing these things are congruent. They never mentioned mid-segment, but what they show are congruent parts, which means E's a midpoint and D's a midpoint as a result of that, because it's just by definition right here, by definition of midpoint. That does mean, therefore, DE is a mid-segment of the triangle. And then, and then CB is parallel to DE by the triangle mid-segment theorem. So they get to use, it's not even the converse, I guess. I would have thought it would have been the converse. But if DE is a mid-segment, then it is therefore parallel. I thought they were going to go more in terms of, there are other forms of proofs that they have, basically. I think we have to learn triangle similarity first before doing the other proofs here, I'll be honest. So I understand why they probably don't have them. Okay, anyway, therefore these two are parallel here. Okay. Some more modeling with mathematics. Pear Street intersects Cherry Street right here and Peach Street at their midpoint. So Pear Street must be a mid-segment. Your home is at point P right here. You leave your home and jog down Cherry Street. You jog down Cherry Street to Plum Street. Over Plum Street to Peach Street. And up Peach Street to Pear Street, over Pear Street to Cherry Street, okay. And back home up to Cherry Street, about how many miles did you jog? The information we have are these mileages bits here. So I can foretell what they'll put here. What if this is a midpoint or mid-segment, what have you, then these are both 1.3s, so 2 of those is 2.6, plus this 1.4 would be 4. Now, 2.25 is this entire distance here, so we've got to take half of that, which is 1.125. So together, that's 5.125. Pear Street should be half of 1.4, which is 0.7. So that's 5.825, I believe. And back to 1.3, that will be 7.125. I think I did that right now. Let's look at what they said. Yeah, 7.125. So it's just a matter of what's going on. 1.3 is half of this, and this is half of the 1.4, and half of this is 1.125, and you can calculate those the way that they put them right there. So about 7 miles is what they say. Okay. All right, guys, we're going to jump straight into this stuff here in a little bit. We got the vocabulary and core concept check to answer first. The blank of a triangle is a segment that connects the midpoints of two sides of a triangle. It's all about that word mid-segment. By the way, I don't know if we're going to do compass construction, but if we do, it's based off finding the midpoints, which you can find using perpendicular bisectors. Basically, we can construct these as well. I almost expect to see it, but I don't know for sure. Complete the sentence. If segment DE is the mid-segment opposite segment AC and triangle ABC, then DE and AC are parallel, and DE is half of AC by the triangle midsegment theorem. So DE, oh my goodness, so DE would be, say, this guy, and then AC would be this guy. They're parallel, but this is also half of that one. So the big triangle's ABC, DE is the midsegment. All right, guys, let's go into the problem set. Now, there aren't very many problems for this one, but it's probably one of those things where, therefore, we're going to have to do a lot. I'm not really sure. I haven't done them yet. Looks like we do start with graphing, though, so I have to prepare myself in that way and get graph paper. Make sure you print out some of the graph paper that I provided for you if you want it to match what I'm using. Otherwise, if you have your own, fantastic. Otherwise, if you're not doing these problems, skip to the next section of problems that you will have. But we are only doing problems 3 through 27. 25 problems. Here we go. Number 3 through 6, we're going to use the graph of triangle ABC with mid-segments. Oh, let me just copy this over, or... I actually don't know if I need the graph paper. You might have to draw it in. But use the graph of triangle ABC with mid-segments, DE, EF, and DF. So they tell you they're mid-segments, and they're marked. And we could show the mid-segments ourselves, but... Oh, we are going to show that ourselves later. We're going to find the coordinates of D, E, and F. All right, well, this is straight up. If it's drawn for us, we can use that. 1, 2, 3, 4, and 1, 2. So D is at -4, -2. E is at -2, 0. It's interesting that they actually give them to you, because I'd imagine, well, I guess I understand it, because they want you to show that these things are mid-segments, but if we found them ourselves, then we would be showing their mid-segments by what we found. So I suppose it does make sense that they're going to give them to us. But that's number 3 already. Number 4, we're going to show that DE is parallel to CB, and it's half of CB. Basically, 4, 5, and 6, we're going to take each individual mid-segment and show that they are indeed mid-segments, that they at least satisfy the theorem of what mid-segments are as well. So let's check DE to CB. So as far as DE goes, we want to know that it's parallel to it and that it's half its distance. So the slope of segment DE is going to be up 2 over 2, which is 1. And we need to see that the slope of segment CB would be the same. We go up 4 over 4, which is also 1. So there's the first show. We got parallel lines there. You know what also was helpful for getting that 2 and 2 and that 4 and 4? And again, I know that the book does more of the actual distance formula, but the distance formula is a derivation of Pythagorean theorem, which is showing that you have right triangles here, and we need to basically find, excuse me, we have like a squared plus b squared. We got to find c squared. Now, you're going to learn this stuff later as well, as far as it's called a 45, 45, 90 degree triangle. I already know what these lengths here will be. But for the length of segment DE, DE squared is 2 squared plus 2 squared. A squared plus b squared is c squared. Those are those lengths. Anyway, I was saying that when I counted up and over, that helped me get those lengths as well. I can use that without having to do a big subtraction. So DE squared is 4 plus 4. DE squared is 8. And DE is the square root of 8, which is 2 root 2. That's that length. CB squared is 4 squared plus 4 squared. 16 plus 16 is 32. And the square root of 32 is 4 root 2. So, showing this, again, same slope, parallel, and DE is indeed half of CB. DE is 1/2 of CB. So there we go. Now we get to do the same thing for all the other ones. I don't know if I can really bring down the image, so I'll probably just look at the one on the side over here, but number 5. So EF, now we're going to look at these ones. So EF and AC. So let's start by kind of doing a count for the, not just for the slope. Remember, it kind of goes in two forms here. Doing the slope also kind of gets you those down and over bits. So we get to go down here and over here. Let's kind of erase the green. Go down 4 over 1. And here you get to go down 8 over 2. I mean, I think that in and of itself kind of lets you know that they go halfway here, because 4 is half of 8 and 1 is half of 2, things like that. So yeah, there's triangle similarity would indeed indicate in these right triangles that yes, this would be half the distance. But here the slope of segment EF is -4 over 1, which is -4. And the slope of segment AC is -8 over 2, which is indeed -4. So once again, parallel. And then as far as distances go, the length segment EF, again, EF squared. Well, you know what? I'm going to skip the squared part. If you want to go in distance formula concept, that's fine. We'll take the square root now, but it's still this squared plus this squared, right? So -4 squared plus 1 squared. And it's not necessarily a requirement here that you need to say -4. -4 squared is 16. It's still positive 16 there, but you get the square root of 17. And the length of segment AC is going to be the square root of, we get -8 squared plus 2 squared, which is the square root of 64 plus 4, square root of 68. Now the square root of 68, you know, I think we had an example in the example thing. This is root 4 times root 17, which is 2 root 17, which means that once again, EF is half the length of segment AC. Like that. So that's number 5. Number 6, DF parallel to AB. Let's see here. Now we're talking about these guys, DF and AB. So let's count those lengths. Down 2, right 3. 1, 2, 3. And down 4, right 6. I honestly didn't count. I just assumed it would have to be true. So let's go ahead and see how that works. The slope of segment DF is down 2 over 3. And the slope of segment AB is down 4 over 6, which is also -2/3. So once again, parallel. Parallel means same slope. We've been doing so much on opposite reciprocal slopes, we then have to remember that parallel is same slope. Anyway, so the length of segment DF, we have, again, square root of, we can just work off this guy here, square root of -2 squared plus 3 squared. So square root of 4 plus 9, or root 13. We're going to expect to get 2 root 13 for the length of segment AB, but it's going to be worked out the way that it works out. -4 squared plus 6 squared, which is 6 square root of 16 plus 36, or square root of 52. 52 is 4 times 13. Root 4 is 2. You get 2 root 13. And 2 root 13 is double that of root 13. So DF is half the length of segment AB. Okay. Those satisfy that. I don't know if it's satisfying those are mid-segments, but that's what mid-segments have by definition, right? They said they were mid-segments, and we found out that they're half the lengths, satisfying our theorems. I don't know if it's proving them because it's using numbers, but it's satisfying them. All right, number 7, or rather in exercises 7 through 10, segment DE is a mid-segment of triangle ABC. We're going to find the value of x. Now, if you're doing these problems, as always, you'd want to copy down a diagram. So here I go, copying down said diagram. We have this here, and we're going to find x. So x is going to be half of 26. Segment DE, let me write it this way. Segment DE is half of segment BC. X is half of 26, which is 13. This is because we know DE is a midsegment of triangle ABC. Only because of that can we say that, right? Number 8. Sorry, I'm copying the diagram. All right. Number 8, AB, the side of the triangle, is going to be double its midsegment, so double the length of DE. So AB is double, or X, excuse me. X is double 5, which is 10. And I know these are probably ones that you could say in your sleep or what have you, right? They're ones that you're like, I finished the answer well before you even copied and pasted the thing. I understand that. But we're putting in the proper math bits as well to feel pretty comfortable about the notation. Maybe you're still practicing the geometry of it all. All right, number 9. We are trying to find, now here, DE is a midsegment, which would break these into two congruent parts right here. So AE's length should be the same as EC's length. Therefore, 6 is X, or X is 6. Straight up. Not half of it. They are the same because E is a midpoint of AC, as DE is a midsegment. And then number 10, I mean, we're motoring pretty fast here, which is good. Obviously, later problems get a little longer, but good start. Number 10, same thing, right? Oh, let me bring the thing over. DE being a midsegment means these two would be congruent here, so the length of BE would be same as the length of EC. Therefore, X is the same thing as 8. X is 8. All right. Okay, let's keep going. Numbers 11 through 16. Segment. Okay, so they're showing some things that are congruent here. XJ is congruent to JY. Let's mark some of the. Well, I'll copy this over. Is this a kaleidoscope? No, this is like a lunch tray. It always comes out kind of big. Let's see. All right. So XJ. Can you use green? Will that show up? What's a color? Red? Yeah, it shows up. Congruent to JY. YL is congruent to LZ. And XK is congruent to KZ. All right. That allows us to note that these are midsegments. JK is a midsegment. JL is a midsegment. LK is a midsegment. They are both parallel to their sides opposite them, and they are half those distances. Copy and complete the statement. So start with the parallel part. So copy down. Segment JK is parallel. Where's JK? JK is parallel to, over there, LZ. Hold on. Not LZ. YZ. Okay. Number 12, segment JL. JL is parallel to XZ. You want to name the full triangle here. The full side of the triangle. So then that way we can say midsegment and side opposite. Even though it's parallel to another segment like that, we really want to get deep into the triangle bit. Segment XY. XY is the full side. That should be parallel to this midsegment LK. Segment XY is parallel to LK. 14. Segment JY is congruent to. So notice there are two congruent marks here, but 3 different segments that can be congruent. So why do they say that? Okay, JY is right here, right? Boom. Now we know that it's congruent to XJ. XJ because J is the midpoint of those two, right? So those two are congruent for sure. But LK is also going to be congruent to those two because if you kind of keep in mind here, LK is half of this entire length, so half of one of these should be equal to it, right? Being a midsegment is half that distance, so they are all congruent in that, right? And we're going to kind of see the same thing with these other ones as well. So number 15, segment JL, JL being the mid-segment this time, JL is congruent to the two broken up portions of the segment that's, or the side of the triangle opposite and parallel to this. XK and KZ. XK and KZ. Segment. And finally, number 16, segment JK, also a mid-segment. JK is this guy. We can say YL and LZ are congruent to it. YL, LZ. All right. Okay. There are those ones. Going pretty fast. In exercises 17 to 19, use triangle GHJ where A, B, and C are the midpoints of the sides. I want to keep reminding you that there are different ways that they're showing that things are mid-segments without calling them mid-segments. So in this case here, they do it just by stating midpoints. In the last set of problems, they did it by stating congruency. In the first set of problems, they did say straight up that they were mid-segments. First sets of problems. All right. Now, these were not in the examples, but we've seen examples like it before, at least if you've been with me for different sections or you've seen them from like 6.3 and 6.4. So, again, mid-segments would show congruency to these parts here. And, you know, we could go, now that we've kind of spoken about this more, you could also indicate that these are congruent, these are congruent, these are... You can do as much as you're able to if you really do make sense of what you can mark up. And this will help me probably answer all that we need to. All right, number 17, AB is 3x plus 8. And GJ is 2x plus 24. Now, they want to find the length of AB. So AB is not the same as all of GJ. It's only the same as one of these two, GC or CJ, but two of these is one of those, right? We could say that AB is, GJ is double AB. So 2x plus 24 is double 3x plus 8. You also could have said that AB is half of GJ. Sometimes I don't want to do that if I think I'm going to run into a fraction. It didn't look like this would have been a fraction, but let's play it safe. Let's distribute the 2 here, and we get 6x plus 16. I get to subtract 2x from both sides, subtract 16 to both sides, and divide both sides by 4. I get x equals 2. But I got to find the length of AB, and I'm going to substitute 2 in for x. You cannot substitute it into either one because AB is just half the length of GJ, unless that's what you end up computing. Just plug it into AB's thing, and you get 14 just units. They don't seem to have any sort of units laid out for you guys here. So that'll be it. All right, so number 17. Let's look at number 18 with the same figure. I have to write these down here. We get AC is 3y minus 5. And HJ is 4y plus 2. By the way, don't assume, I don't know, but don't assume that we're using any of these same variables or lengths as before. I don't know if they're even going to relate, but that's okay. We got to find the length of HB, So HJ is the entire side right here, and AC would be half that length, or HJ is double that of AC, right? We said that before. So HJ is double that of AC. So 4y plus 2 is 2, 3y minus 5s. Let's go. 4y plus 2 equals 6y minus 10. If you distribute, subtract 4y, add 10, divide by 2, you get y is 6. Now we need to find the length of HB. HB is... You have a couple things you can do here. You can take the length of HJ and divide it by 2, or take the length of AC, which would be the same as it. Since we haven't said a half thing yet, let's just do that. Let's say that HB is half the length of HJ, which is half of, so there are a couple things we got to do. 4y plus 2, but substitute the 6 that you got for y. 4 times 6 plus 2 like that. So half of 24 plus 2. Or half of 26, which is 13. I hope I didn't mess anything up along the way there. I probably went kind of fast on the algebra. I think everything panned out fine. 24, 26. I think so. Sorry, that was number 18. Whoa, what is that? Number 19 comes next, and I probably just got to paste in this thing again because I'm going to go to another page. No congruence marks anymore. Hope that's okay. Let's see if we can just work off that. Number 19. GH, the length of GH is 7z minus 1. And the length of CB is 4z minus 3. Let's find the length of GA. So GH is this whole guy here. CB is this little guy here. Now, I was actually inclined to do one of the half ones here, but this time I wouldn't want to do a half because it would lead into a fraction. 7 and 1 being odd numbers. So anyway, GH is double that of CB, or 7z minus 1 is double that of 4z minus 3. So 8z minus 6. Subtract 7z from both sides, I get z. Add 6 to both sides, you get 5. Z is 5. Let's find the length of segment GA. Just this guy right here. That should be the length of CB. This time, let's do it that way. GA's, and look, you get a, I don't know if it's a rhombus, you get a parallelogram right there. You might know about parallelograms, you might not. GA is the length of CB. In this case, we get to do 4 times 5 minus 3, or 20 minus 3, which is 17. That is GA. Okay. All right, we are rolling, guys. Number 20. We're only a half hour in. Number 20, describe and correct the error. I mean, it doesn't look like a mid-segment, but I never go by that. Let's see what they said. DE is half of BC, so by the triangle mid-segment theorem, segment AD is congruent to segment DB, and AE is congruent to EC. Okay. If DE was a mid-segment, for sure, then that would actually be true, that you would have those congruent marks. But the drawing is trying to indicate something. It's trying to give you a hint and indicate something for you. It's very possible that DE is half of BC. It's very possible to have something half that, but not be the mid-segment. In order to be the mid-segment, DE must also be parallel to segment BC. So, although DE is half of BC's length, it is not necessarily parallel to BC, and nothing indicates that. If it is not parallel, then it is not a mid-segment. And if it is not a mid-segment, then we can't conclude. Congruency. Basically the congruency that we had. Now, whenever they say correct the error, it's hard to correct unless they gave you more information. So my correction based off the information they gave you is we don't know whether or not they're congruent. And another correction would be to correct the problem, not really, but to say I would need to be told that DE is parallel to BC. So it's kind of hard to state a correction for. Now keep this in mind, guys. I want you to keep this in mind. It's possible that AD is still congruent to DB. But in fact, it's possible that they're both congruent. But they'd only be congruent if the things are for sure if the things are parallel. So even if they're not parallel, it's possible for one of them to be congruent. And if, the other could be congruent on its own as well, even if they're not parallel. That's possible. Wait. Maybe not. I take it back. Maybe not because of this length being half. I'm going to actually say maybe not in that case. But they're only congruent together if those are parallel. All right. Ooh, now you're talking my language. Baseball, number 21. The distance between consecutive bases on a baseball field is 90 feet. Agreed. A second baseman stands halfway between first base and second base. I don't agree. Because now you're saying the first baseman maybe stands here. A shortstop stands halfway between second and third. Maybe this is where they're positioning for the play. Okay, for the sake of the play. And a pitcher stands halfway between first base and third base. Find the distance between the shortstop and the pitcher. Okay. So we want to find this. Okay. I don't know if I want to copy it over. I'll just refer to the diagram if I have it. So we know that 90 feet would be any of these entire lengths here. Any of them. That includes this one right here. These are all 90 feet. Sorry, not all of them. This one and this one. Sorry, I just got to use that with my mouse. Now, if this is 90 feet, then this, being a mid-segment, we know it's a mid-segment because shortstop is halfway between, should be half of 90. So, distance between shortstop and pitcher is half of distance between first base and second base, which is half of 90, which is 45 feet. And you need the units there. Is that all they needed? Find the distance between shortstop and pitcher. Yeah, it's just half of that, just based on the mid-segment things. Hopefully you're okay with you're hearing what I say. Blah, blah, blah. Shortstop and pitcher, first base and second base. All right, that's a pretty quick question. I want to do more with baseball. Use the figure from example 2 to prove the triangle midsegment theorem for midsegment DF, where F is the midpoint of segment OC. Okay, see example 2. All right, give me a second. I'm going to go and find this example again. Example 2. Oh, it was the one where they did the coordinate proof. Let me copy it over. DF, I guess F is down here. It's going to be. All right, let's see. 22. Okay, use the figure from there to prove it for DF. F is the midpoint of segment OC. Okay, here we go. So F is going to be this guy. Now the ordered pair of F would be, now in D we can also find out as well, right? It's going to be half these distances. Halfway between 0 and 2Q is Q. Halfway between 0 and 2R is R. We want to do it for midsegment DF. And F, halfway between 0 and 2P is P, and halfway between 0 and 0 is 0. So we know those right there. So here's a new midsegment. We need to show that this guy, let's use the line tool, this guy is the midsegment of BC. And clearly I didn't draw this to scale there. Okay. All right. Not to scale, but it didn't even look parallel. Okay, so first thing I want to do is find the slope of segment DF. In order to be a midsegment, it needs to be parallel. This needs to be parallel to this, and this would need to be half the distance. So the slope of segment DF, this is where I actually have to get a little more mathy. So y2 minus y1 is r minus 0. I want to find the distance from r to 0 and the distance from q to p. y2 minus y1 or x2 minus x1. So q minus p, like that. So it's going to be r over q minus p. Now the slope from b to c, we got to do, again, a y2 minus y1 to r minus 0 over x minus x1, 2q minus 2p. 2q minus 2p. That's 2r over 2q minus 2p. You get a common factor of 2 all throughout here. So you can divide all these by 2, and you get r over q minus p. That means these are the same slope, which means these are parallel. So just from getting the midpoints, I can use those midpoints to then calculate that slope. Now it's about distances. The distance from D to F, it's the square root of, I might as well use distance formula now that it's all variables. X2 minus x1 squared, so q minus p squared plus, and then y2 minus y1 squared, r minus 0 quantity squared. And, you know, honestly, I didn't pay attention to see what they did. If they I don't know if they expanded this out or not. I'm going to say probably not, but we'll see. Square root of q minus p squared plus r squared. For now, I'm going to leave it like that and see if I can leave it like that. and not have to do more. We'll see. The length from B to C is the square root of, oh, we might have to do more than that. Let's see. 2q minus 2p quantity squared plus 2r minus 0 quantity squared. See, before, oh, you know what? Before they got to just use the flat side, so they got to use the ruler postulate or whatever they called it. They didn't have to do this right here. So this is the square root of 2q minus 2p squared plus 4r squared. So 2r quantity squared is 4r squared. I feel like I have to do more for these based on what's provided. So let me give some more room. I want to simplify the inside squared quantity here, that root q, that thing there. Let's see if I can get more out of it, because I don't think it's enough to prove that the things inside here are the same until you see more, I guess. So this is going to be q squared. This is a binomial that you can square. So minus double the product, 2 times q times p. I'm used to the p being first, plus p squared. And then there's that plus r squared. So that's all those guys together. That's another way of putting it. And this one is the square root of, we have 4q squared minus, and then we get to double. Here we get to double 2q times qp. So that's 8. Oh, sorry, I don't want to write the double part. Doubling 4qp is 8qp minus 8qp plus, and then I get 4p squared by squaring 2p, and then there's the plus 4r squared. Now, once again, this doesn't necessarily show that that's half of that from what we have, but I'm content with what I have there. Here we got to still just do more. Here, 4 can factor out of all of these terms, and that's important to state, because if you can factor out a 4, then you can take that 4's square root. So in here I'd have q squared minus 2qp plus p squared plus r squared. And that 4, again, can be square rooted. Remember, what you can do here is we can take the square root of 4 and the square root of this separately. I'll leave this inside the square root, but that square root of 4 turns into a 2 without being inside a square root anymore. So this then becomes 2 times the square root of q squared minus 2qp plus p squared plus r squared. So this is a better way of simplifying that. And if this is double it, right? 2 times root q squared, and check out this one. This is 1 times root q squared minus 2qp plus p squared plus r squared. So they are the same, except this is double that. So BC is double DF, or DF is half of BC. I think that goes to show that. So parallel, half the distance, therefore mid-segment. Yes. Okay, the longest problem we've had so far. There's number 22. I wish the baseball one was that long. Number 23. Looks like it's still kind of on a graph. Let's see if we have to use that. XY is a mid-segment of triangle LMN. Suppose DE is called a quarter segment, basically a mid-segment of a mid-segment. What do you think an eighth segment would be? Make conjectures about the properties of a quarter segment and an eighth segment. Use variable coordinates to verify your conjectures. I have to do coordinates and verification? No, at least these ones are flat against here. So let's start with just answering the quarter segment part. 23. Quarter segment. Now, they say make a conjecture, right? Yeah, a conjecture is something you believe to be true, but you haven't yet proved it. You've seen examples to indicate as such, or a visual. So we know that if XY, for example, is a mid-segment of LN, then XY is not only parallel to it, but it's half the length of LN. Now, DE is parallel to LN as well. Right? DE being a quarter segment is parallel to LN, but it's quarter the distance from LN. It doesn't seem to be quarter the length, though. Looks like maybe this one would have been quarter the length, but if I'm at this one, it looks like it's maybe 3/4 the length. So my conjecture is that segment DE is parallel, is still parallel to ln. That hasn't changed. And DE is 3/4. This is my conjecture. 3/4 the length of ln. So that's where I'm going with that. Okay. Seems to make sense, and honestly, I don't see a reason it won't be true. By triangle similarity, these should be in proportion that way, so it's probably right. Now, as far as this goes, let's add some coordinate points for these. I want to do these in this kind of same way that they did it before. You want to use, like, because I'm going to do quarters of things, actually later I'm going to do eighths of things. I might want to make things 8 times bigger. Like, instead of 2p, let's use like 8p and stuff, because we're going to have to use that later. So I'm going to put L as 0, 0. I'm going to put N as, and I forget what letters. I think they used, here they used Q. I think here they use P. So let's call N 8p, comma 0, and it gets to be 0 because it's still on the x-axis there. Now, M is at totally different variables. So, like, but I can still make them 8 times bigger of something. So, like, I think they use Q. So 8Q, and let's say 8R. What happened to my pen? Before I was a pretty pen, now it's this crap. Let's at least make it blue. All right. So let's do those. Now, so for D and E, we could figure those out by finding midpoints of midpoints. If we call this thing a quarter segment, we're going to have to work this thing out in such a way. We can't just say it's going to be a quarter of it. We're calling it a quarter segment, but it's based on the way that it's made here. So here's what we got to do based on all that. Let's find X and Y. X's midpoint will be averaging 0 and 8Q, which is 4Q. I should probably just write it on there. And Y averaging, and X's Y values from 0 to 8R, that's going to be 4R. Y's midpoint goes between 8Q and 8P. Let me actually show the math for this. 8Q plus 8P divided by 2, averaging those, and 8R plus 0 divided by 2. Obviously something I don't need to put, but I will. Which is, now you get to divide those by 2, so 4Q plus 4P divided by 2, and then this is 4R. Excuse me, not divided by 2. Now that you divided it by 2, it's just that. So 4Q plus 4P and 4R. So those are those guys. Now we need to find the midpoints between X and L and between Y and N. So just half of those, averaging these guys. So D is going to be 2Q, comma 2R, right? And then Y is a little bit trickier. We don't take half of, E. You don't take half of these ones right here, because this was half of these because it's halfway between 0 and 4Q and 0 and 4R. But E is halfway between this 4Q plus 4P and 8P. Yeah, so I think I really got to do the math on that one. So 4Q plus 4P plus 8P divided by 2. This other one's a lot easier. From 4R to that is also 2R. That shouldn't change. But E is going to be at 4P plus 8P is 12P. So 4Q over 2 is 2Q. And 12P over 2 is 6P. So there's E's coordinate point. So D and E look like that. And we're going to have to use those for the 8th segment eventually as well. So here's what we have to check. The slope of segment DE is 0 because this is a horizontal line. The two R's are the same. That's fine. The slope of segment DE is 0. The slope of segment LN is 0. Those are fair enough. Horizontal line. Okay. Distance-wise, we get to use that ruler postulate. Basically, we don't need to compare the y's. The y's are just 0. We don't need to use whole distance formula. We just have to subtract this distance from that distance. So the length of segment DE is going to be, we're going to take 2q plus 6p and subtract 2q. So subtract those and you get 6p. Now the length of ln goes from 0 to 8p, which is 8p. My conjecture was that the length of DE was 3/4 of ln. Well, 6p is 3/4 of 8p. And that does check out. So, that is true. Parallel, that is true. Therefore, yes, it is a quarter segment, and that is what a quarter segment, that's what a quarter segment would do. My conjecture holds up. All right, let's do the 8th segment. Now, I don't think I have to do quite as much, or maybe I do. At least we have the idea of what to do, and we can label parts that we already have. See, the 8th segment, I have to do another labeling. In here, I'm going to have to make a whole nother line. And the 8th segment looks like it gets to be even closer to ln. So hopefully you can kind of make the similar-ish conjecture with me. Let's see. What letters? Let's use F and G. F and G. Okay. So FG would be an 8th segment halfway between L and D. F is halfway between L and D, and E and N, things like that. Now, mid-segments aren't as cool. Mid-segments get to make a whole mid-segment triangle like that. Quarter segments don't get to do the same thing. Like another quarter segment here would have been there. Another quarter segment here would have been there. So they probably don't get to make a triangle within, but these probably have their own little thing to play with here. All right, D was this guy. E was this guy. So it's good to probably copy and paste those over. Keep those ones in mind with the ones that are already labeled. Sorry that I feel like I'm going more slowly on this problem. I really want you to process it, and I want to make sure that I don't mess up one of my letters and that I have all my diagram flowing here. I hate when this does this sometimes, sorry. I have an extra comma floating in space. All right, so there's D and E. Let's talk about F and G. F is the midpoint of segment LD, so halfway between 0, 0 and 2Q and 2R. This is where you get Q and R. This is why I went to 8 times bigger, so that I could avoid fractions. G is halfway between E and N. Now, the easy part is the R for the Y value. The X value is where you have to average these 2Q plus 6P plus that 8P all divided by 2. Because you're averaging this X with that X. So 6P plus 8P is 14P. 2Q divided by 2 is Q, and 14P divided by 2 is 7P. So Q plus 7P comma R. So there's my F, there's my G. Okay, we have to check the slope of FG. Straight up, guys, I think we can understand with R being the same heights, this will be 0. So the same thing with segment LN. I'm sorry, I did not make a conjecture yet. Let me do that. Conjecture is going to be that segment FG is parallel to segment LN. And this time, being another just an 1/8 away from there, I'm going to say that the length of FG is 7/8, the length of LN. Basically, it's however far away it is, you subtract that from, it's whatever's remaining from there, right? If it's 1/8 away, then 7/8 of the value. So that's my conjecture. So let's find the length of FG. We already know the length of LN as 8P. So the length of FG, we get to take Q plus 7P and subtract Q from it. The Q's cancel, and you're left with 7P. And the length of LN, we already said was 8P, and we can see that. Now it looks like, is FG 7/8 the length of LN? Well, 7P is 7/8 the length of 8P. And yeah, 7P is 7P. That one checks out. Therefore, that one also holds up. So parallel and that. Verified. All right, let's keep moving forward. Number 24. I thought I was going to finish in less than an hour, but that last couple problems kind of added time. Find a real-life object that uses midsegments as part of its structure. Print a photograph of the object and identify the midsegments of one of the triangles in the structure. Well, obviously I can't do this on the internet. I could if I go to Google and find something, so I'll think of something. I don't know if they mean... It sounds like they say triangles as well. So it doesn't need to be like an object that you pick up, right? It could be something like you saw other ones that were from like a bridge or something like that. I gotta think something in life that even has triangles. Print a photograph. Identify the mid-segments in one of the triangles in the structure. It literally says structure, so we're probably thinking more buildings. Let me just pause and think about what does, and then I'll come back to you. All right, so I did a quick search. Honestly, I didn't find much. I mean, I'm positive the design of bridges, and I think they talked about roof trusses before, right, for houses. I'm sure those are used in architecture all the time. The only one that I found that's kind of like whatever is like this sitting swinging chair thing. Yeah, things like that. I mean, I don't really know if there's anything that structurally it's important that this thing is a mid-segment right there to make it happen, and it only uses one of them. It doesn't use like all three. So I don't know. This is one that I'm kind of skipping. You know, I don't really have much to say on it. It's not even thought-provoking so much. I'm not saying it's not thought-provoking, but it's something where you would find one as opposed to think about why one. I don't know. All right, I'm just going to move forward. Number 25, abstract reasoning. To create the design shown, shade the triangle formed by the three midsegments of the triangle. Then repeat the process for each unshaded triangle. Do they want me to do it, or they're just saying what I think they just show you what it looks like. Okay. What is the perimeter of the shaded triangle in stage 1? Oh, okay. Yeah, they have numbers. I was going to say, how would I know unless I make one? I got to sneeze. Excuse me. Okay. So I'm just going to... Stage 1. I was copying down stage 0. My bad. Let me do this again. Well... Here, let's just mark on here. So what do they want? What's the perimeter of the shaded triangle in stage 1? Well, in stage 0, these are all 16. So what we first made were mid-segments, which make all these 8s. There are two ways to do it. You can just do 8 times 3 right here. Stage 1 perimeter is 24. You could also... take half of the perimeter of the first one. Part B. What is the total perimeter of all the shaded triangles in stage 2? They still have the stage 1, 1. So those are the 8s there. But then these are mid-segments of those within. So these are like 4s, right? 4, 4, 4. And so would all the other ones. So stage 2 perimeter. So we have a few things here. We have the 24, and then we have 3 different ones where we're multiplying 4 by 3, right? Because there are 3 different triangles of those perimeters of that. So we have 24 plus 12 plus the 36, which is 60. Now, I don't know what the pattern is here yet, but we did do 24 plus 36. 36 is 50% more than 24. So part C, what's this total? Stage 3 perimeter. It's more of the same. We get our 60 plus, and then all these little guys here. So these are 2s. 2, 2, 2. Now, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times the 2 times 3 there. So that would be 60 plus 2 times 3 is 6, and 9 is 54, which is 114. Now, this went from 24 and then to 36 and then to 54. 54 is 50% more than 36, etc. Now, they didn't ask, but stage 4 perimeter, instead of just saying from 114, I would say this. It was 24 plus 36 plus 54 plus 50% more than 54 is 81. That would be my guess for what the next one would have been, because they seem to be adding and increasing another 50% to their things. This is just a made-up one. And I wish they kind of asked me that. What do I think that would be? Because I think I'd know. So 195 would have been that one. And here's the other thing about perimeter. We still get to add all the sides because they only meet at the vertices of these. That means perimeter's not being covered at all by any of the other triangles, which is something that sometimes is a part of surface area that can get tricky if one surface is on top of another, but that's not the case here. Okay, number 26. How do you see it? Explain how you know the yellow triangle is the mid-segment triangle of the red triangle in the pattern of floor tiles shown. Assuming the floor tiles are the same, what we can say, I mean, there are a lot of ways we can kind of talk about it here. We can look at lengths of these things. Like that length has a gray edge and a white edge, and then there's a gray and a white, things like that. That's probably the way I'd mostly talk about it. You can look at the areas of each of the triangles, all having full gray and then a full white and then 2 half grays, like that. So there are kind of different ways we can do it. So like I said, each triangle, the yellow sides, no, let's see, the mid segments have half the distance of the red segments by as the I don't know, like I said it to you, but it's hard for me to type. As the yellow mid segments have half the red segments. 1 gray, 1 white versus 2 gray and 2 white. I don't know. I don't really know how to say it. Now that's part of it. On the upper left and right, and goes across half the amount of gray squares on the horizontal lines. This is not a good, I can show you visually without typing it. It's really hard to do. But that's just half the distances. That doesn't show parallel lines. The parallel parts are, let's see, the mid segments are also parallel to opposite sides because they traverse the same parts of tiles together. So what I mean by that, I'm not going to type anymore, but what I mean by that is in red, you're traversing the actual edges of the tile, you know, the squares right here, and same with on the yellow, it's traversing edges like that. And because these are squares, then these would have parallel bits to them. And then same with going here, they traverse across corners together from gray square corner to gray square corner, and same with this, gray square corner to gray square corner of squares that are all oriented the same direction. So that can only apply to be parallel with that. I'm really bad at the description stuff because I could type all day, but I want to point to things as well. So obviously it's hard for you to say, well, how am I going to write it? I mean, you know, this is the part where this is a solution guide video, sure, but I'm teaching you. I'm not telling you how to do everything. I want to teach you how to come up with things yourself. So really open-ended, come up with it yourself. There are a lot of different ways. And remember, I could have mentioned how the triangles were all the same area kind of thing. A whole white square and then 2 half gray squares and inverted and all this stuff. All right, last one. Attending to precision. The points 2, 1, 4, 5, and 7, 4 are the midpoints of the sides of a triangle. Graph the 3 midsegments, then show how to use your graph and the properties of midsegments to draw the original triangle. Give the coordinates of each vertex. Okay, so I get to actually use a graph for myself this time. I don't know if it's whoopee, but I get to. Yay, I get to do it. Now, I hope these don't go... that these midsegments won't, but I hope that the triangle ones won't actually go away from the... that I can fit them all, you know? So here's P, Q, and R. Okay. When it comes to, and let's connect them. When it comes to finding the actual triangle made around this, you have to remember that these are parallel to the sides of the triangle. They're also half the distances, but I think we can figure out that half the distance thing once we track the parallel bits. But these are also the midpoints. So here's really what I'm going to do. I mean, I can almost literally do a copy-paste job. I'm going to look at, for example, you see this QR? This slope, the slope of QR is down 1 and over 3, negative 1/3, like that. So from P is a midpoint of a mid-segment going this direction. And remember, QR would be the same as half of the length of whatever this P thing would be. So if I went down 1 over 3 like this, I would have another segment that would go like that. It's not a mid-segment, it's a part of the triangle. And then another one, if I went up 1 and left 3 like that, and it would make this thing here. So a couple 1/3s in this direction would lead to these points of the triangle right here, here, and here, because QR should be parallel to it and it should be half its distance. So I'm kind of showing it to you based off nature of the slope. And I can do the same thing with PQ being 2 of these guys over here. I mean, I'm literally copying and pasting right now, but that's up 4 over 2. And then this, just do another up 4 over 2, like that. And that would land me on this point. And then obviously the third one I could just connect all those. Those should be collinear. But we can use this and copy and paste it as well. Again, you don't get to copy and paste, but count it. We're going up 1, 2, 3 over 1, 2, 3, 4, 5. And then up 3 over 5 again. I'm just connecting those things up and boom. There, I get a triangle that's based off that. Now, give the coordinates of each vertex. I'm going to call this triangle ABC. So triangle segment A is at negative 1, 2. B is at, and it fits, 9, 8. And C is at 5, 0. Now, they didn't ever say explain. They said show how to use your graph and the properties of midsegments. That's what I'm showing. It's that slope thing right there, right? So it's how much you rise and run from those and kind of just double them up. Just know that these are the midpoints of them. So you get to go up and over and down and the other way. And then you can kind of get them. And they should all meet at those parts. Those are coordinates. They didn't ask for distances of any kind. And that would be that. So guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. This is one of my shorter videos, or at least as of recent. I was hoping it'd be less than an hour, but some of the problems took a little bit. If you need anything else from me for this section, please let me know. But thank you so much and take care. I will see you in the next one.